Good morning. Welcome back. I hope you guys are all doing well, staying safe, and ready to roll for the best class of the day. I'm looking for Alex, Alan, Leo, Micaiah, Crisscross Joseph, Tristan. Nidal just popped in. Hi, Nidal. Please try to get here a couple minutes earlier. Philip and Faith. If you're here, please let me know. All right. Let's see what's happening for the best class of the day. Here we go. Welcome back. Quote of the week is dream big. Whatever you want to do in life, go out there, set your goals, set your dreams high, set your bar high in life, and accomplish those dreams. Live a fulfilled, full life. Use your potential. Today's Wednesday, June 9th, 2021. Today's day one. We're going to continue on unit number 11 in nuclear chemistry. It's going to be a relatively light day. What's going on? We're going to finish up topic number 3, fusion. We already went through fission. We'll finish up fusion. We'll go through the guided notes on fusion. We'll watch a few YouTube videos on fission versus fusion. We'll analyze some nuclear power as well. And then we'll work on the exit pass. So that is the agenda for today. Tomorrow, you are going to have your final exam for Regents Chemistry. Your final exam is going to be 30 multiple choice questions, Regent style questions. The exam is going to be on Buzz. We'll talk about details and password sensitivity, all that stuff tomorrow. So you have the full block to complete the 30 multiple choice questions. What I would have for tomorrow is a calculator, a reference table, scrap paper, and a pencil. Have those 4 things for tomorrow too. What's going to be on the exam? The final exam is going to cover anything from unit number 1 all the way to unit number 11. So I'm not going to review again. I just reviewed for the post-test. So review is on yourself. If you want to review, go for it. But we just reviewed as a class together. Yes, 30 multiple choice questions for the exam. Regent style questions. Hey, Faith. Does anybody have any questions on the final exam? I would not focus or give much attention to unit number 11. Our initial plan as a department was to have unit number 11, topics 1, 2, and 3 on the exam. But when I scanned through the test quickly, it didn't look like there's any questions in nuclear chemistry. So I would suggest, I've been saying unit 1 through 11, but it looks like it's only units number 1 through 10. You should be aware of what we're doing right now in class because we're doing it right now in class in the event there's questions on nuclear chemistry. Any questions for me? Maybe you're sitting at home, you're wondering, hey, what's going to happen after tomorrow? Is the class over? Well, first off, you have to take the final exam. If you don't take the final exam, your whole average is going to be destroyed. If you don't take the final exam tomorrow, you get a 0 there, it's going to mess your whole average up for the year. So make sure you take that. After the final exam, there's not many days of school left. So after the final exam, what's going to happen? We're actually going to finish up the rest of this unit. We'll go through half-life, 1 class. The next class will go through radioisotopes. And then once we're done with that, it'll take us to the remote days for June 18th and June 21st. Those remote days, the 18th and 21st, what we're going to do, we're going to analyze chemistry and society. One day we're going to watch a whole video on nuclear weapons in society. It's going to be the entire block. Nuclear weapons in society. I would have played this throughout the duration of the year. The last day, we're going to analyze the effects or plastics, the impact of plastics in society, organic compounds has on society. So we'll watch that for the last day of school. And there will not be any questions for either one of those video sessions. It's more of a reflection of thinking, hey, how does this chemistry incorporate with real world? Atoms, they make up everything. They'll give you a different perspective on things too. So that's the plan for the rest of the year. Yeah, you're gonna have to turn in your guided notes. Those will have to be turned in at the completion of the unit. Micaiah, please try to get here a few minutes earlier. And Alan, hello, welcome. Please try to get here a few minutes earlier too. All right, let's get to it. Please open for guided notes. Let's figure out what we're talking about with nuclear chemistry. And we already went through topics 1, topics 2, topic 3 we'll finish up today. Topic number 1, we talked about nuclear stability. We talked about topic number 2, which was artificial and natural transmutation. And we also talked about topic number 3, fission and fusion. Yeah, this is the last unit, Jimmy Law. This is the last unit. We're done after we finish these last 2 topics here. And another thing, this would have been all the content I would have covered throughout the regular duration of the year. So I'm happy we all got through all the content together. My curriculum was very similar to how it would have been traditional school year. But the only thing different, I think you guys all know, the only thing different is you would have had more labs. Yeah, it took a lot of time to complete these notes. I'm proud of you guys for doing this. A lot of you guys did great work with completing it. I told you in the beginning of the year, this is what drives our course. If you understand our notes, you complete your notes, you're engaged with the notes, you understand the examples, you draw the pictures for the notes, then you'll understand your examples, you understand the exit pass, you'd understand the benchmark exams, the midterm, and then your final exam you'd understand too. Hopefully you feel that way. If you're doing what I asked you to do, I'm betting you feel that way. If you just logged into Zoom all year, said, see ya, you probably got nothing out of the course. But here we go. Let's go through it. We talked about nuclear stability, topic number 1. We talked about radioactivity, when an unstable nucleus gives off radioactive particles and or energy. We talked about an unstable nucleus, unstable atom. An unstable atom is going to have an atomic number greater than 82. An unstable atom is going to have a proton to neutron ratio that is out of 1-to-1 ratio. If it's a 1-to-1 ratio, it's stable. If it's not 1-to-1, it's going to be unstable. We talked about particles that are released with radioactive emissions. We talked about alpha, beta, positron, and gamma radiation. We talked about table O. We talked about these particles. You should know what an alpha particle is. Alpha particle is going to be 4/2 or a helium. We said a beta particle is going to be 0/-1. That's negatively charged. Gamma is energy, 0/0. We talked about neutron, 1/0. A proton's 1/1. And a positron, we said, is 0/1 in standard notation. We talked about the charges. We put a particle through a medium, and then it went through a magnetic field, a positive and negative charge. You were able to predict the following. You were able to predict which one attracted towards the positive charge. You knew this charge had to be a negative, therefore it had to be a beta particle. You analyzed the one that went right through the magnetic field, and it was neutral, didn't get deflected, that was a gamma ray. And the last one on the bottom, you analyze that one, the one deflected towards the negative had to be the opposite charge of a positive. So we analyze that just like the Thomson's experiment, cathode ray experiment. Alex, please try to get here earlier next time. Leo, likewise, please try to get here earlier next time. Only a few more days left, guys. It takes a lot of time for me to think about all this stuff and go back and forth. We talked about radioactive decay gives off a lot of energy. That's what we're focusing on today and yesterday. We talked about mass defect, where a small mass gives off a ton of energy. We talked about balancing a chemical equation. We did that. Topic number 2, we talked about artificial and natural transmutation. Think of the word transmutation. Oh, transmutation. You're transferring an element and mutating it to something else. Transfer, mutate. Think of those words. Break them on up. You're changing the identity of an element to something else. Natural transmutation. This happens automatically. Spontaneous disintegration of a nucleus of a certain atom causing a release of particles or energy. Break it up. Automatically breaking up of a nucleus and energy is released. we looked at some examples. Let's take a closer look today. We looked at some examples of natural transmutation. An element goes and changes to another element, transfers to another element. One element transfers to another element. They're different identities, and something is released. Something's emitted. A positron is emitted. Oh, transmutation. One element transfers to another element. Something is emitted. Yeah, transmutation. One element, Pu, stinks, changes to another element, U, and something's emitted. What's emitted here? It's an alpha particle. Alpha particle is released. Pu changes to uranium. It transmutates to another element. Something is released. Natural transmutation. Look at it again. Neon changes to sodium, transfers to a new element. Something is released. A beta particle is released. Last example, natural transmutation. Nitrogen changes to oxygen. Within that process, of that transfer, something is emitted. Something or particle is going to be given off. A beta particle is emitted. Natural transmutation is going to always have this format. That's an equation, natural transmutation. Element changes to another element, some sort of particle is given off. We talked about artificial transmutation, where a human-made reaction is bombarded, in which a nucleus is bombarded with a high-speed particle, causing a particle to be given off. A man-made reaction where a nucleus is smashed with a particle, it changes and a particle is given off. Why are they important? Because man-made elements, human-made elements come from these. They're elements in the actinide series of the reference table. We looked at some examples of artificial transmutation. Natural transmutation, elements to another element, something's released. Artificial transmutation examples are a little bit different, not much. Let's look at the second example. We have an element, Al, changes to another element, and something's released. A neutron is released. A neutron is emitted. Artificial transmutation. You're taking an element, you're taking a particle, this is an alpha particle, you're smashing it or bombarding, you're humanly bombarding the nucleus of aluminum. You're smashing the alpha particle with the aluminum, and that's going to create a new element, and something is released. So it's kind of similar to natural transmutation, but we're bombarding it. This is definitely an artificial transmutation. The next example, we have an element, converts, transfers over to another element, transmutates to another element, and something is emitted. This would be natural transmutation. Third example, we have an element, transfers to another element. It's definitely transmutation. But we have a beta particle in the reactant side. So PM is reacting with the B, the beta particle. It's going to smash into the nucleus here. It's going to break it up. It's bombarding, and then ND is going to be produced. The other thing that would be produced here would probably be gamma energy. This would be artificial transmutation. And the last one, hopefully for artificial transmutation, you could analyze an element, converts to another element, and something's produced. That tells us it's transmutation. ES transfers over to MD, a neutron's produced or emitted. But before we took the ES, we took the alpha particle. Those two things reacted. That alpha particle smashed into the nucleus of ES. This caused a reaction. The alpha particle smashed in or bombarded the ES and produced MD plus a neutron. That is artificial transmutation too. Are you going to have to identify anything like this on the final exam tomorrow? No, probably not. Most likely, no. So the final exam is 30 questions. We had to like pick, one of the teachers had to pick 30 questions throughout the duration of the year. I didn't make it up. I just know you guys, if you pay attention, you should be able to do it. Topic number 3, we talked about fission versus fusion. We talked about fission. A few people told me what the definition of fission was. We defined it. We found a picture of it. And then we said, hey, fission is the splitting of a large nucleus that produces a lot of energy. We talked about the capturing of a neutron to create 2 smaller isotopes or 2 smaller atoms. We know the fission reaction deals with uranium plus a neutron yields krypton 92 plus barium 141 plus 3 neutrons plus a ton of energy. Fission reaction deals with uranium. Mass is converted to a ton of energy. This is the atomic bomb. We know a fission reaction is a chain reaction. This one reaction is going to take place. It's going to continue to react until it gets stable. We talked about an uncontrolled fission chain reactions, a nuclear explosion. A controlled fission reaction is a great source of energy. So there's differences with the fission reaction. One's controlled, one's not controlled. All right, today's class, we're going to start off by defining, just like we did last time, we're going to define fusion. So with a Chromebook or cell phone, the online version of the textbook, we're going to define fusion. Once you define fusion, you're going to find an image that represents or something that you can relate to that would represent a fusion reaction. So please do so in the notes next up. Please find it below. Just trying to edit my notes here. Use your cell phone or Chromebook, whatever review book, define fusion, and you're to draw a picture or find a picture online of fusion of what it looks like. So we're doing the exact same thing we did last time. This should be fusion. What it looks like right there. Once you define it, please put your definition in the chat. So again, define it. Probably take the Chromebook, define it, put your definition right there in the notes. Find an image that represents fusion, and then please put in the chat. It's 12:01. I'll give you to 12:06. Okay, a couple people defined fusion for me. Thank you for putting it in the chat. Fusion, hopefully I have a definition that is similar for this than when you look for it as well. Notice fusion, you thought about fusion. Some of you guys found fusion like the phase change for fusion. Guess I should have told you nuclear fusion. Nuclear fusion, it's a little bit different. So Jumiloff found the definition, the process by which two or more atomic nuclei join together or fuse to form a single heavier nucleus. During this process, some of the mass of the fusing nuclei is converted to energy, which is released. Cool definition, nice, very good definition. Nadina said that a reaction in which two or more atomic nuclei are combined to form one or more different atomic nuclei and subatomic particles. Good, that one works too. Both of these definitions, you can find the common bond here, the common trend. You can see fusion is combined, Nadina said, and Jumila said fusion is joined together, or she said fuse. So yeah, the common thing, you're definitely joining together, you're fusing, you're combining the things together to make one product or one bigger thing. You're joining together, fusing something together means taking something and combining it or fusing it together. Maybe you know that term. Fusion is definitely going to be combining. Your drawing, hopefully found a drawing on the web for fusion reaction or nuclear fusion. Type a new folder, add a new folder, add to toolbar nuclear fusion. Find an image that you can think of that relates to you, that you understand. So maybe you don't really know what deuterium or tritium is. I'm going to take this image right here. Right? Because it tells me, oh, hydrogen and hydrogen. You can use any one you want. Find an image that you could start off with. I'll take that image. I'm going to copy that image. I'm going to paste it within the text box. Yeah, if you had a hard copy, you could draw that. But we're different. We could just copy and paste right from the internet. Boom. That's the image I want to look at for fusion. Maybe you started to think about this process. What is fusion? Yeah, it's combining. You already know that one from the definition. But a fusion reaction, what's going on here? You're taking a tritium. So let's write this out for a second. What's tritium? It's telling us right there. Tritium is H3. It's an isotope of hydrogen. So tritium is going to be hydrogen 3. What's an isotope? It's the same proton number, but a different mass. What's an isotope? It's the same element, but a different mass. An isotope, the same atomic number, but a different neutron number. There's several definitions for an isotope. There's your tritium, hydrogen 3, plus, you can see there we're adding it together, plus deuterium, hydrogen 2, deuterium, 2/1. The proton number is the same, mass is different, another isotope. Yields, those two things combine, they fuse together to make a helium. Helium is going to have a mass of 4. The proton number is going to be 2. And a neutron. So helium plus a neutron is released. Oh, neutron. Do you remember the notation? Let's figure it out. Oh, we have 2 plus 3 on the left for the mass. That's going to give us 5. The mass on the right, the product side must be equal to 5, 2. So it's going to have 1 over, do the same thing with the proton number, the atomic number. 2 on the left. We need a total of 2 on the right. So proton number, atomic number for a neutron is 0. It should be 1/0. The last thing that is missing from this, once you have this chemical reaction, you're going to have a ton of energy given off. Energy is released here. That is a fusion reaction. You're taking a hydrogen plus another hydrogen. You're combining them together to make helium, a neutron's released, and energy is given off, a lot of it. Let's watch a flick, and then we'll jump into the notes a little bit more.
The concepts of fusion and fission have been considered for hundreds of years. In the past, it was called alchemy, but the goal of an atom. Fusion is when create a nucleus of greater mass. All elements exist because fusion from hydrogen atoms created larger atoms up through lead. Stars are powered by fusion, creating helium and other elements, and supernovas create the heavier elements. Fusion requires very, very high temperatures in order to occur. We're talking over 40 million degrees Celsius. This is what's happening in our sun, so the high temperatures make sense. Let's look at a reaction that occurs in the sun. Deuterium is an isotope of hydrogen with 1 neutron, and tritium is an isotope of hydrogen with 2 neutrons. When they collide under high temperature conditions, they form a helium atom with 2 protons and 2 neutrons. They release a neutron, written with the lowercase n for the symbol, and they release a huge amount of energy. Now, it would be amazing if we could harness this massive release of energy to feed our need for electrical energy, but we run into 2 problems with fusion. Fusion requires temperatures that are very high and very difficult to attain, and the reaction itself is nearly impossible to control. To get the high temperatures to start the reaction, we need something like a nuclear bomb, and once that's going, good luck trying to control it. Fission is, in a small part, the opposite of fusion. It's the splitting of a nucleus into smaller fragments by the release of neutrons and lots of energy. But nuclear fission will only happen when neutrons hit one of 2 fissionable isotopes, uranium-235 or plutonium-239. First, a neutron hits uranium-235, which makes it so unstable it breaks into 2 smaller parts, and also releases 3 neutrons. If these neutrons hit other uranium-235 atoms, it can start a chain reaction. A chain reaction is where fission releases neutrons, which hit other fissionable atoms, producing more neutrons, which can react with even more fissionable atoms, and so on and so forth. We can harness the energy released from fission much more easily than harnessing fusion's energy. Nuclear reactors are the heart and soul of nuclear power plants. We use controlled fission in fuel rods that are cooled by a coolant fluid, usually water. The heat from the core is used to generate steam, which will drive a turbine that creates electricity in a generator. The large towers that you may be used to seeing are actually just for cooling down and condensing the water so that it can be reused in the system. There's no radioactive material in those cooling towers, just steam. The fuel rods are made of a metal which contains uranium-235 or plutonium-239. When the fuel rod is low in fissionable atoms, it's considered to be spent, used up. Spent fuel rods are still radioactive, so they must be placed underwater in holding tanks to cool them down, and the water also acts as a shield to reduce radiation levels. The rods glow blue because of Cherenkov radiation. The rods can also be stored here for many years, and may later be recycled or moved to a more permanent storage location. Now, perhaps most notoriously, fission and fusion can be used in nuclear weapons. The fission bomb, also known as the atom bomb, includes weapons whose explosive output is exclusively from fission reactions. Many fission bombs have been dropped to test and study their power and nuclear fallout, which is the radioactive contamination that's left in its wake. Only 2 fission bombs have been used in warfare, and thankfully, none have been used since. Thermonuclear bombs are weapons that use fission to trigger fusion reactions with tritium, deuterium, or lithium deuteride. In order to get the fusion reaction started, a fission reaction must occur first to create the high temperatures that are needed. The fusion reaction doesn't create nuclear fallout, but the fission reaction does. Thermonuclear bombs are the most powerful and potentially destructive nuclear weapon. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe, and follow me on Twitter at SciencePet.
Boom, there you go. Fission versus fusion. Hopefully that give you a little bit more insight on the impacts of nuclear energy or fission versus fusion. Let's jot down some notes on what this is. So please open up your guide notes. Back to this. Here you go. Fusion. A lot of you guys, a couple of you guys already defined it. Nice. That works out well for us. A fusion reaction. We know it's going to be combining. I'll highlight my bold. You know my format. The combining, the combination of a nucleus of a small atom to form a larger atom. A process that releases a lot of energy. So a lot of you guys, your definitions were pretty darn close. Just talking about energy. Your definitions were fine. Combining of a nucleus of a small atom, small atoms, to form a larger atom, a process that releases a lot of energy. The example is deuterium, tritium fusion reaction. The example that we talked about. What happens here? In this chemical reaction for fusion, paint can. There it is. You're taking isotopes of hydrogen. We're going to take H3, 3/1. Control period brings it on up. Control comma brings it on down. Isotopes of hydrogen. We're going to add them together, fuse them together. So hydrogen 3 plus hydrogen 2, control period, 2, control comma, 1. Hydrogen. You add those two things together to yield to make helium. 4 is a mass, 2 is a proton number for helium. This element is definitely going to be He. Plus, what else was released? We had a neutron release. What's a neutron? Mass of 1. Atomic number 0. They ask you which two subatomic particles have the same mass. You're going to tell them a proton and a neutron. They both have a mass of 1. Electrons are so small they orbit around the nucleus. The last thing given off here is a ton of energy. Energy, a lot of energy in a fusion reaction, a lot of energy in a fission reaction. Which one gives off more energy? The fusion reaction. Again, I think of fission as the atomic bomb. I think of fusion as the sun. The reactions on the sun gives off a ton of energy. Fusion reaction should have isotopes of hydrogen to produce helium and a neutron. There's a chemical reaction. The problem with a fusion reaction for creating energy, for restoring energy, converting it to energy for electricity, it takes a high energy. It takes a lot of high temp and high pressure to create this. High energy requirements. In order for the nucleus to combine, in order for the nuclei to combine, these nuclei are going to need enough energy, a lot of energy, enough energy to overcome the force of repulsion. You're forcing these two things to come together when they don't like each other. Overcome the force of repulsion. What does that mean? So basically, if you have two magnets, you have two north ends of magnets, we know that the two north ends don't attract. The opposites repel. Opposites attract, likes repel. That's what I meant to say. Opposites attract, likes repel. If you have two protons two positive charged protons, they're not going to attract to each other. They're going to repel each other. So in order to have a fusion reaction, these nuclei have to combine. There has to be enough energy to force these two things, the two protons, to like each other, to smash together, to get together and combine. The magnitude of the repulsion increases with its charge, and only small nuclei with small charges can be used for fusion. That's why fusion reactions are not going to be bigger elements. They have to be very light elements. Temperature degrees. There's a typo here. The temperature of 10 to the 9th power, that's got to be raised up. There's a typo there. Not 109. It should be 10 to the 9th degree Celsius are needed to have enough activation energy, are needed to have the activation energy for a fusion reaction. If you read the article I sent you guys the other day, I sent you an article on China, how they reach a really high temperature. That's a really big milestone for us. Why? Because they're trying to get to a fusion reaction. We're trying to get fusion energy to be manageable so we can use it for electricity. Why is fusion energy better than fission energy? Look at the products we have for fusion. We have helium and a neutron to create energy. A fission reaction, if you look at the products for a fission reaction, we have smaller isotopes or radioactive isotopes. The problem with a fission reaction, it gives off radioactive particles, and nobody wants this radioactive particle in their backyard. They have to do something with this waste. What are they going to do with this waste? You're not going to want it in your backyard. No, I'm not going to. So that is a big con for a fission reaction. Where do we store this radioactive waste? Nuclear energy. Nuclear energy releases, bless you, nuclear energy. The energy released in a fusion reaction is greater than the energy released in a fission reaction. Energy released in a fusion reaction is greater than the energy released in a fission reaction. You know what that means? That a fusion reaction gives off more energy than a fission reaction. How do I think of this? I think of a fusion reaction being the sun. That big sun out there gives off a ton of energy. That big mass in the sky, that bright mass, that fusion reaction in the sky gives off more energy than the atomic bomb does. Yeah, fission, I think of the atomic bomb. You saw pictures of the atomic bomb. That gives off a ton of energy, but not as much energy as the sun. So definitely think of fusion as the sun, huge chemical reaction up there, and fission as the atomic bomb. Which one gives off more energy? The sun. So what we're trying to do with this fusion reaction, this energy, is we're trying to mimic reactions on the sun. The sun's going to have high temperature, high pressure up there for the reactions to occur. That's why it's so tough for us to get to these temperatures, these pressures, to create clean energy. The difference in mass is the amount of mass that was converted to energy. Energy equals mass times speed of light squared. That's Einstein's formula. Energy equals mass times speed of light squared. You'll analyze that chemical, or the equation, not chemical equation. You'll analyze this equation in physics next year if you decide to take it. E equals mc squared. Let's watch one more flick and then we'll analyze some questions. That's it for notes for today, though.
Many of you have heard the terms nuclear fission and nuclear fusion before. Nuclear fission means the splitting of atomic nuclei. This is the process by which energy is generated in nuclear power plants. With fusion, it is exactly the other way around. Here, the atomic nuclei amalgamate. One result of nuclear fusion shines down on us from the sky. This is the energy that stars like the sun emit. But what exactly happens in these two processes? And why is so much energy released in the course? To be able to understand this, we first have to recap what the structure of an atom looks like. In the center, there is the atomic nucleus. That is to say, the thing that is split or that amalgamates with another nucleus. Nuclei consist of neutrons and protons. The protons are positively charged. The neutrons have no charge, hence they are neutral. Thus, the atomic nucleus as a whole is positively charged. Around the positively charged atomic nucleus, so-called electrons are whirring around, like in a kind of cloud. They are negatively charged. So now let us look at what happens when nuclear fission takes place. Here, the atomic nucleus is hit by a single neutron that is flying around. The impact causes the atomic nucleus to split into two new nuclei. Each of them takes part of the electrons with it, so that two new atoms are formed. In the case of some very large atoms, a few neutrons are additionally released. When uranium atoms are split in a nuclear power plant, this usually involves the release of 3 neutrons. These can then affect the next fission processes in a chain reaction. Energy is released, and very much of it at that. 1 kilogram of naturally occurring uranium has the energy of 12,000 liters of mineral oil, or of almost 19,000 kilos of hard coal. But where does this energy come from, and why is it so much more than in the case of other energy carriers such as oil and coal? Let us recall, besides the neutrons, the atomic nucleus only consists of the positively charged protons. Now, equal charges repel each other, similar to the equal poles of 2 magnets. The fact that the protons in the atomic nucleus remain together, nevertheless, is due to the so-called strong interaction. This is one of the 4 fundamental forces in the universe, and by far the strongest. By the way, this force used to be called nuclear force, or strong nuclear force. It acts like a strong rubber band that holds together the atomic nucleus with its protons, which we know do not really want to hang around so closely together. When the impacting neutron forces the nucleus apart, it is exactly the energy that has been stored in the rubber band that is released. This energy is not released upon the burning of coal or oil. In this case, there are chemical reactions developing in which the atomic nuclei are not touched and where only electrons are exchanged. Nuclear fusion presents a similar picture, or rather, a mirror image. It only works with small atoms, like hydrogen, for example. The atomic nucleus of the latter consists of only 1 proton. If one now tries to force 2 of these protons together, these 2 would have to repel each other due to their equal charge, as in the case of magnets. When talking about atomic nuclei, this is referred to as the so-called Coulomb force. This force acts as if each of our protons had a fence around it, trying to keep off other protons. Like fission needing a force that overcomes the rubber band of strong interaction, fusion also needs one that forces the protons so closely together that the fences are pulled down. And once this happens, and the protons come too closely together, strong interaction comes into play again, and makes sure that the 2 amalgamate into a new atomic nucleus. As in the case of the nuclear fusion on the Sun, it is in fact 4 hydrogen atoms, that means 4 protons, that amalgamate to form a helium atom. But as the latter only has room for 2 protons in its nucleus, the other 2 are released, similar to the excess neutrons upon the fission of uranium. And of course, this also involves the release of a lot of energy, even more than upon nuclear fission. It would only need 1 single gram of fuel, or the hydrogen isotopes deuterium and tritium, to gain as much energy as from 12,000 kilos of hard coal. This is why scientists try to develop power plants in which energy is won from nuclear fission. But how is the Coulomb force, meaning the fences around the protons, overcome? This happens by speeding up the atomic nuclei, and that happens when they are subjected to great heat or pressure. The more pressure is available, the less heat is needed. Sooner or later, 2 atomic nuclei will hit each other at such great speed that the force of the impact will overcome the Coulomb force, and the protons will no longer repel each other. This is also what happens in the Sun, where 15 million degrees and a pressure of 200 million bar are necessary to amalgamate the hydrogen atoms. In a fusion power plant on Earth, We would even need 150 million degrees, as we have a lower pressure than inside the sun. However, to this day, we have not been able to generate such high pressure in a fusion power plant. If you would like to learn more about this topic, just watch our videos. What actually is radioactivity, or types of radiation?
All right. Hopefully you got some more information.
Many of you have
Video.
heard the terms nuclear fission
And
and
you can
nuclear
watch it
fusion
again.
before.
And again and again. Please open up the Exapass. Let's go with the Exapass on fission versus fusion. We will do the even questions to get today together. And then once we're done with that, I'll give you some time to complete the odd questions. Get a little odd today. All right, so please open up Exapass, unit number 11, topic 3, fission versus fusion. We only have 2 more Exapasses after this throughout the year. That's it. Crazy year, 2 more Exapasses, which I'll probably do with you or assist you. Maybe you want your guided notes handy. Maybe you don't want them. Maybe you want to see how you're going to do. We'll do the even questions. Question number 2, it says, which process occurs in a controlled fusion reaction? Oh, you have to differentiate between fission and fusion. You should be aware, what is fission, what is fusion? We're talking about a fusion reaction. Oh, fission is a splitting of an atom. Fusion is the joining, combining of an atom. All right, so it's got to be joining or combining. Not splitting, no. Definitely not splits. So it can't be C, it cannot be D. Collide to produce a heavier one. Oh, let's read some more. Oh, we're taking a smaller atom, combining them to fuse them together to make a larger atom. Oh, collide to produce a heavier nucleus. A light nuclei collides to make a heavier nuclei. 2, the best answer is going to be choice A. 2 is A. Next up, number 4, we're doing the odd questions. Maybe you want to do the even questions right now. It's up to you. Number 4, which equation represents a fusion reaction? Oh, fusion reaction, you're thinking about you're combining 2 things. Let's start there. Combining 2 things. Okay, we're taking 2 things to combine them to make something else. Okay, could be that. Choice C is not combining anything. It's taking a PA and it's going to make a new element. Something is released. A beta particle is released. That is a natural transmutation. Choice D is an element transfers to another element, transmutates to another element. Something is released. That is natural transmutation. Choice B would represent an element being bombarded with a particle. A new element is formed, something is released. That is artificial transmutation. Fusion reaction, you're fusing 2 things together. You're taking the H, you're taking the H, you're combining them together to make a helium, plus a neutron should have been represented here. And energy, it's not always represented as energy. Think of fusion as hydrogen isotopes. Fusion, hydrogen. Fusion, hydrogen. Fission, uranium. Number 4, the best answer is choice A. Yeah, you could find that in the notes too. There's similar isotopes. There it is. It's got to be H's converting to helium all the time. 4 is A. Number 6, it wants to know what should be represented by X. What's represented by X here? Which particle is represented by X? Oh, that's easy. We did transmutation last time. We filled out and figured out the missing link last time too. Solve for X. What's going to go there? Oh, last time we figured out the masses on the reactant side had to equal the mass on the product side. We also figured out the proton number on the reactant side had to equal the proton number on the product side. That was easy. We took 2 plus 2, added them together to give us 4. We said 4 equals, oh, this math is super simple. 4 equals 4. The mass number has to be equal to 4. We took the bottom numbers. We said the proton number is 1 plus 1. There's 2 on the left. It must be equal to 2 on the right. 4 over 2, that element is going to be kind of funny. It's helium. Helium is produced. Or 4 over 2 would be an alpha particle. Looks like choice D is the best answer right there. How'd you know it's helium? Proton number of 2 tells us it's helium. Or you could check out table O. 6, the best answer is choice D. Next, even question number 8. Given the nuclear reaction, this equation is best described as what? Please record your answer in the chat. What kind of reaction is this? Please record your answer in the chat. Once you have an answer, 21 people on live right now. Hey. Hey, guys. What kind of reaction is this? That element is key. Oh, thank you, Santino. I have 21 people live online, and somebody in class gave me the answer. What is it? Oh, we're 0 for 1. Oh, 1 for 2. 2 for 3. We just went 2 for 3 just now in class. Hopefully you guys at home have some sort of answer. You have uranium. Uranium is key here. Uranium is going to be a fission reaction. So if you're thinking fusion is uranium, no, don't. It's opposite. Fusion has that U in there. Fusion's going to be the hydrogen. But thank you for your answers. So fusion has isotopes of hydrogen. Fission has uranium. There's my uranium. Boom. Uranium fission reaction. 8 is A. You could easily pull up your notes and say, oh, which one has uranium? Uranium, oh, there it is. U. It's got to be fission. U, fission. 8 is A. Next, number 10. Tricky question here. Which kind of reaction is represented by the equation? Please record your answer in the chat. Thanks, Adina. Wendy, this is your question. Sorry, I get crazy with my cursive. Oh, C. Wendy said C. Fission reaction. Uranium is fission. Fusion is isotopes of hydrogen. 10, the best answer is going to be choice C. 10 is choice C. Real quick, throughout the year we talked about chemical reactions. What kind of chemical reactions have we talked about? We talked about an addition reaction. Hey guys, don't really do the spotlight on me all the time. But we talked about an addition reaction. Two things come together to make one compound. Addition or synthesis. We talked about decomposition. A compound breaks off to two smaller things. We talked about single replacement, where an element plus a compound yields a new element plus a new compound. That was substitution as well. We talked about double replacement. A compound plus a compound yields a new compound plus another new compound. So those are the first four that we talked about. Then throughout the year, we talked about more reactions. We talked about a redox reaction. What's a redox reaction? It's Leo says Ger. Loss of electrons and the gain of electrons is oxidation. Loss of electrons, oxidation, gain of the electrons, reduction. Leo says Ger. Spent a whole unit on redox reactions. We talked about neutralization reaction. What's a neutralization reaction? An acid plus a base yields salt and water. What other reactions did we talk about? We talked about reactions in organic chemistry. We talked about saponification, the process of making soap. We talked about fermentation, the process of making alcohol. We talked about polymerization, the process of making a long chain. We talked about esterification, the process of making a smelly fragrance or an ester. And then we talked about transmutation, natural and artificial transmutation. And then we just talked about the last two reactions, fission and a fusion. Those are the chemical reactions you should be aware of for tomorrow's final. Probably wouldn't focus on organic reactions as much. But those are all the chemical reactions. You should be aware of what they are. All those chemical reactions. Next up, here we go. Number 12. It wants to know this diagram. The diagram shown demonstrates a nuclear reaction in which a neutron is captured by a heavy nucleus. Which type of reaction is illustrated by the diagram? All right, we have a nice visual here. Let's analyze this visual. We have a neutron. There's a neutron. Boom. We have a heavy nucleus, a heavy element, whatever. And then a neutron's going to hit this heavy element. There's my neutron. We'll say it's right there now. Once that neutron bombards that nucleus, it's going to start to separate. You can see a little confusion starting to separate here, a little movement going on. And then it's going to really separate, like in cell division, cytokinesis. And then it separates to two smaller elements. So from here to here, you're taking an element and converting it to two smaller elements, and you have some neutrons produced. What kind of reaction is this? Please put the answer in the chat. What do you think is going on here? What kind of reaction is represented? One for one. If you're at home participating, the sooner you guys can work, the sooner we get through this. Please respond your answer in the chat, something in the chat. Faith, what do you think? B, someone said, a couple of people said B. An exothermic reaction is a fission reaction. We're taking a neutron, we're bombarding the neutron with a heavy nucleus to create two smaller atoms. You're splitting here. It's definitely splitting. So what's going on? You're splitting, you're breaking up the heavier nucleus to two smaller ones. Which one's splitting? You guys defined it. It's definitely gonna be a fission reaction. And Faith knows that fission reaction creates a ton of energy, and energy is going to be released. That is a fission reaction. Heat is released. Exothermic reaction. Heat is given off here. So that would represent a fission reaction, just like the equation in the notes. Definitely the best answer is choice B. Last question here, number 14. Should be an easier one now after you saw that last one. 14, here we go. Accompanying diagram represents a nuclear reaction in which a neutron bombards a heavier nucleus. What kind of reactions represented there? Analyze it. You have uranium, you have a neutron. So it starts off with a neutron being smashed into uranium. This causes some confusion with the uranium. It's embedded in there. It creates two new elements and a ton of energy is given off. I think you guys know this one by now. Uranium, that's key there. I'm not going to draw the key again. Uranium is a fission reaction. Best answer there is going to be choice A. Best answer is choice A. Okay, guys, I'm going to give you 5 minutes to work on the odd questions. Maybe you already did it. So 5 minutes, please work on the odd questions for topic number 3, the exit pass. I'm going to put you in a breakout room. If you have any questions, feel free to ask for help. I'm going to be here. I'll give you 5 minutes right now to complete it. It is, we'll say 12:50. I'll give you till 12:55 to do that. Please complete this assessment. If you don't finish it, it's due by Saturday. You have from now till 12:55 to complete it. Please join the breakout room. Please complete
and
Only 2 more topics, that's it. This year. About 20 seconds left for people to finish up or get out of the breakout rooms. 10 minutes left of class. I'll take 5 minutes of yours. Maybe 6. All right, hopefully you finished up the exit pass. If you did not, it's going to be due by Saturday. Only a couple more exit passes left for the year. Real quick, though, I do want to just go through this. This is the entire year of chemistry. This is the units. This is the topics that we went through. So again, we went through unit number 1, science of the verb, done. You know those topics. Unit number 2, matter and energy. What was covered? There it is. You went through that. We went through the atom. We went through the periodic table. We went through chemical bonding, which took forever. We went through properties of solutions. We went through all these topics in kinetics and equilibrium. We went through redox. Went through acids and bases. Organic chemistry, we just finished. And here we are at the end of the year. Just finished fission and fusion. We have 2 more topics left. We'll get there. All right, to wrap up today's class, I'm going to play one more video. It's going to be on nuclear energy. That's going to be it for today's class. So here you go. Enjoy this video on nuclear energy.
we found it frustrating and confusing, so let's try and get to grips with this topic. It all started in the 1940s. After the shock and horror of the war and the use of the atomic bomb, nuclear energy promised to be a spin-off of the world get back on its feet. Everyone's imagination was running wild. Would electricity become free? Could nuclear power help settle the Antarctic? Would there be nuclear-powered cars, planes, or houses? It seemed that this was just a few years of hard work away. One thing was certain, the future was atomic. Just a few years later, there was a sort of atomic age hangover. As it turned out, nuclear power was very complicated and very expensive. Turning physics into engineering was easy on paper, but hard in real life. Also, private companies thought that nuclear power was much too risky as an investment. Most of them would much rather stick with gas, coal, and oil. But there were many people who didn't just want to abandon the promise of the atomic age, an exciting new technology, the prospect of enormously cheap electricity, the prospect of being independent of oil and gas imports, and in some cases, a secret desire to possess atomic weapons provided a strong motivation to keep going. Nuclear power's finally came in the early 1970s when war in the Middle East caused oil prices to skyrocket worldwide. Now, commercial interest and investment picked up at a dazzling pace. More than half of all the nuclear reactors in the world were built between 1970 and 1985. But which type of reactor to build, given how many different types there were to choose from? A surprising underdog candidate won the day, the light water reactor. It wasn't very innovative, and it wasn't too popular with scientists, but it had some decisive advantages. It was there, it worked, and it wasn't terribly expensive. So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water's used to drive the turbines anyway. The light water reactor became prevalent because it's simple and cheap. However, it's neither the safest, most efficient, nor technically elegant nuclear reactor. The renewed nuclear hype lasted barely a decade though. In 1979, the 3 Mile Island nuclear plant in Pennsylvania barely escaped a catastrophe when its core melted. In 1986, the Chernobyl catastrophe directly threatened Central Europe with a radioactive cloud, and in 2011, the drawn-out Fukushima disaster sparked new discussions and concerns. While in the 1980s 218 new nuclear power reactors went live, their number and nuclear's global share of electricity production has stagnated since the end of the 80s. So what's the situation today? Today, nuclear energy meets around 10% of the world's energy demand. There are about 439 nuclear reactors in 31 countries. About 70 new reactors are under construction in 2015, most of them in countries which are growing quickly. All in all, 160 new reactors are planned worldwide. Most nuclear reactors were built more than 25 years ago with pretty old technology. More than 80% are various types of light water reactor. Today, many countries are faced with a choice: the expensive replacement of the aging reactors, possibly with more efficient but less tested models, or a move away from nuclear power towards newer or older technology with different cost and environmental impacts. So, should we use nuclear energy? The pro and contra arguments will be presented here next week. Subscribe, and then you won't miss it. Our channel has a new sponsor, Audible.com. If you use the URL audible.com/nutshell, you can get a free audiobook and support our channel, producing our videos.
All right, guys, that's going to be it for today. We'll obviously explore the problems with nuclear weapons or nuclear energy on those remote days. Final exam tomorrow, 30 questions, 3 multiple choice questions. Have scrap paper, reference table, calculator, pen or pencil for class tomorrow. All right, guys, that's it. Have a good day. We'll see you later. If you have any questions, feel free to hang out. Bye. See you later. Have a good day. Nice, Santino. They're off.